Hey guys, so in this video we will be talking more about Bohr's model and how Bohr's model is used to explain the energy spectrum of hydrogen that we see when we run energy through hydrogen gas. When we run energy, then we see those spectral lines, those discrete energies, those discrete colors coming out of the gas. This will explain, Bohr's model will explain why that happens, and so we'll talk about that in this video. The first thing that we have to do, though, is talk a little bit about light, and we'll be talking more about this in our video on the photoelectric effect, which we will have soon. But right now, I'm sort of, even though the photoelectric effect was done before Bohr's model, I'm sort of putting these together in a way that I think makes the most conceptual sense leading into quantum mechanics, instead of by how it was historically. So we'll talk a little bit about the important things about light that we have to understand for this. And the first thing is, hopefully you know, light is in a way both a wave and a particle, and we'll be talking a lot more about that around the end of section 1. And the reason that is, one of the things is it has discrete particles called photons that carry a certain amount of energy. But those particles also, just like a wave, have a frequency and a wavelength. And the energy of a photon, which I'll write is EP, EP, is proportional to the frequency. It's h, which is Planck's constant, times the frequency f, where Planck's constant is about 6.34 times 10 to the negative 34th joules seconds. It's related to h bar, which we talked about in the last video. H bar is Planck's constant h divided by 2 pi. So it's called the reduced Planck's constant. Okay, so now the wavelength and frequency of a wave are related by the equation that the velocity is equal to the wavelength times the frequency. And we know for light travels at the speed of light, c, which is approximately 3 times 10 to the 8th, 300 million meters per second. And c, so c equals lambda f, where lambda is the wavelength of light. And then we can solve for f here and plug that in, so we could write the energy of light in terms of the wavelength, which is hc over lambda. Okay, so these are the important equations about light that we'll need to know for this video. Now, the next thing that we have is I've got the electromagnetic spectrum here. And light waves are called electromagnetic radiation because they're really just fluctuations in the electromagnetic field. You may understand that, you may not. That's not the most important thing, that's just where the name comes from. Depending on the wavelength and frequency of light, and as you can see by this equation, a high wavelength means a low frequency and a high frequency means a low wavelength, and vice versa. So the different types of light have different names and different properties. So if we have a very short wavelength with a high frequency and high energy, it's a gamma ray. Right? Then as you get to a lower wavelength, a longer wavelength, a lower frequency, lower energy, we get to X-rays, then ultraviolet light, then we have this range from about 400 nanometers of wavelength to 700 nanometers of wavelength in the visible light spectrum. Then we have infrared, microwave radiation, and then the longest wavelength with the lowest energy and lowest frequency are radio waves. Okay, so now that we've covered this thing about light, let's look at how Bohr's model shows this. So the first thing is we'll have an electron in the lowest energy level, right? Because that is where things naturally lie. They're naturally around the lowest energy that they could have. But then we run some energy through it, and what that does is it excites the electron. So right now it's in what's called a ground state, and then it gets excited, it bounces up to another energy level, and we'll just say there we're talking about, let's say it goes to n equals 4. But for full generality, I'm going to call this n initial, okay? Because what we're talking about right now is it emits light is it falls down energy levels. So we're not going to talk about how it starts in the ground state, then we run energy through it. So a lot of the times you'll like run electricity through it, and it gets excited. Right now we're just talking it starts at some high energy level, we've gotten it there, and then it's going to fall back down because it turns out the high energy levels are not very stable. The electrons want to get down to a lower energy. Okay, so it starts at this n initial, which here in the diagram it's n equals 4, although it can be in, any different spot, and then it will fall down. But say it starts at n equals 4, well, now it has actually 3 different possibilities of where it can fall down to. It can fall down to n equals 3, or it can fall down to n equals 2, or fall down all the way down to n equals 1. So there's a bunch of possibilities. All we know is it's going to fall down. So let's just say, for full generality, starts at n initial, and then it's going to fall down to some n final, okay? So this is n final. And we'll have the electron here. Okay. So, now looking at this, we can use our idea of conservation of energy, which hopefully you know that energy cannot be created or destroyed. So in mathematical form, that means the initial energy initial, is equal to the energy final. Okay? So, notice it starts with this high energy here, and then it goes down to a lower energy. Well, where does the rest of the energy go? And that's where we have to use a photon, right? Because when it falls down, it has to release that energy somehow, because it starts high energy, it ends in low energy, so it has to release the energy in the form of a photon, which we sometimes write as gamma. Okay? And so now, really, it's the energy of the electron initial is equal to the energy of the electron final plus the energy of the photon. I'll just write it P here. And so this is the total energy initial equals the total energy final, right? Where these E's are just the energy of the electron itself. So what this means, if we rearrange for the energy of the photon, this is E initial, the initial energy, minus the final energy of the electron, right? Which makes sense, that it's the opposite, right? It's the higher energy, the initial energy, minus the lower energy, is that change in energy of the electron, right? So the amount of energy the electron loses, right? This is the amount of energy the electron loses, right? Or you could write it negative delta E, right? So the amount it loses is equal to the amount of energy that the photon has when it's emitted. But we know what E initial and E final are in terms of N initial and N final, right? So we have, this is the energy of the photon. The energy initial is, right, EP equals, we have our negative 2.18 times 10 to the negative 18th joules. Just imply I'll write joules here. Joules over N initial squared. Minus, but then it's minus a negative, so that's just like plus 2.18 times 10 to the negative 18th joules over N final squared, right? Because we're subtracting a negative. And so now we can rearrange this in terms of, so let's write it 2.18 times 10 to the negative 18th joules, it's the energy of the photon, again, times 1 over N final squared minus 1 over N initial squared. And so now, if we transition, right, if we transition from some N initial to N final, we just have to plug it into this equation, and that's the amount of energy the photon releases. And again, we could write this 2.18 times 10 to the negative 18th also in electron volts, which, as we see in this diagram here, is negative 13.6 electron volts. Okay, so all the possible energies that the photon can have are all possible combinations of N final and N initial, right? And so now we can look at what happens. So we have what are called different series when we're talking about this. And so the first thing that we'll talk about this diagram here, is the Lyman series, where the Lyman series is just the energies you can get when n final is equal to 1, when you are dropping down to the ground state. And then you can have all the different n initials. So we have this first energy in the Lyman series here, and as you can probably see, a longer line is a larger drop in energy, right? So a longer line means a higher energy of the photon, which means a higher frequency, which means a lower wavelength, right? So in our diagram, I can just even write these are long lines. And these are short lines. Right? So the length of the line here is really inversely proportional to the wavelength. Right? As it shows the energy difference between the energy levels. So the Lyman series, we can start with n equals 2. So n initial is 2. It starts at the second energy level and drops down to the first. Or we can start at the third energy level, drop down to the first, or the fourth, the fifth. Right? And you can see these energies are all a lot are all very high. So you have very high energy photons released. In fact, these are in, they're not all the way over here. For hydrogen, these are still pretty much all in the ultraviolet range. So you have ultraviolet light emitted. This is not actually visible light. Where you get to the visible light, and this is where we can definitely see, if we saw in the diagram before, is when we get to the Balmer series. Okay? Because the Balmer series is when n final is 2. Right, the Balmer series, n final equals 2. And then the Paschen series is n final equals 3. And I think there are names for the other ones, but right now these are the ones that we're focusing on. But the Balmer series is very interesting because for these first 4, I'm going to try to write this out. It's hard to... These first 4, here hopefully you can see where I did that. These 4 transitions are visible light. Visible light. Like the 5th one in the Balmer series that looks like it's going from n equals 7. It looks like from n equals 7 to n equals 2 appears as though that one is still in the ultraviolet. But if we go from n equals 3 to n equals 2, n equals 4 to n equals 2, 5 to 2, or 6 to 2, those transitions all release a photon in the visible light spectrum. And we can see, if you actually look on the diagram that had those 4 lines when we talked about the spectrum of hydrogen, you can see that that you have those 4 lines. The first one, the transition from n equals 3 to n equals 2, is red. The transition from n equals 4 to n equals 2 gives you a pretty, like a light blue. The transition from n equals 5 to n equals 2 gives you a deeper blue, and n equals 6 to n equals 2 gives you violet. And then, oh, sorry, I think I did that, yeah, no, I did that correctly. And then, yeah, and then the n equals 7 to n equals 2 is an ultraviolet still. So it's high enough energy. So that really confirms it, and that shows, because the Bohr model, actually these energies predict the colors correctly if you put them into this equation, and you can see what those energies are. Use this equation to look at that, and you'll find that those 4 land within that 400 to 700 nanometer range of visible light. Now, the Paschen series, as you can see, these are all shorter lines, so they have lower energy and thus longer wavelengths. These are those energies from n equals 4 to n equals 3, 5 to 3, all of them to 3. Those end up being in the infrared range. So this is a diagram of these are the different energy levels. You can, if you plug them into the formula using electron volts, you'll get that. I don't have the conversion on hand, but that's how you get them. Okay, so these are the energies. We've seen these diagrams, so this should sort of confirm Bohr's model actually has some really good results. And in fact, the equation here is actually the same as you'll get in the Schrödinger equation, which I may have mentioned. Two other things that I want to talk about in this video. One thing is just a brief note. We're doing this for hydrogen, although this actually works for anything that's called a hydrogenic atom, which means it can have any number of protons, so it can be any other atom. This works, Bohr's model works and gives us the correct result for any atom with only one electron. Right, so these numbers will be shifted a little bit. So for example, if we have helium instead of hydrogen, all of these numbers will actually be doubled. So this will have even a lower energy, but you'll have even higher energy differences. So if you had helium, but only with one electron, you'd actually have higher energy for the gaps. And so that's a hydrogenic atom. And so now, the other thing I want to talk about is what is called the Rydberg formula. And the Rydberg formula is like this energy formula for the energy of the photon, but it gives us the wavelength of the photon. Okay, and if you rearrange this, right, you can easily get the frequency of the photon from this. That should not be super difficult. But now we want to look at the wavelength. And now E, we know, is hc over lambda, so let's just derive this Rydberg formula, right? And the reason the Rydberg formula is important is because often we look at like the color of light in terms of the wavelength, and so we want an explicit formula to get the wavelength. Okay, so E is hc over lambda. Let's do that in a different color here. Here, yeah. So E is hc over lambda is equal to 2.18 times 10 to the negative 18th joules times 1 over n final squared minus 1 over n initial squared. And then we can find 1 over lambda equals 2.18 times 10 to the negative 18th joules over hc. But I'm going to call that another constant. That's going to be called r0. And r0, so 1 over lambda is r0 times 1 over n final minus 1 over n initial. And then squared. These are both squared. And this is the Rydberg formula. It gives us 1 over wavelength, but then we can just take the reciprocal of it. And it uses this R0, this Rydberg constant. And the Rydberg constant, R0, and, or actually, oftentimes I've seen it written as R0, although I think, now that I think about it, most textbooks actually use RH. So I'll switch to that. So we have RH. Sorry about that. Is equal to 2.18 times 10 to the negative 18th joules over Planck's constant times the speed of light. And if you plug in all those numbers, we will get we'll get about 1.097 times 10 to the 7th meters to the negative first, so reciprocal meters. Okay, so now we have an equation that we can explicitly find the wavelength of the light emitted. So it's pretty much equivalent to this equation. It's just two slightly different ways. This one just gives us the wavelength directly. And the frequency shouldn't be too difficult to get, right? Because then we just would have to divide the energy by Planck's constant. You can do that, find that equation yourself if you would like. Okay, so that is it for this video, and I will see you in the next video.